So this is the Chapter 19 worksheet for chemical thermodynamics. I'm going to run through this pretty quickly, so some of the definitions or anything like that I'm just going to skip. I'm going to do more visual and math problems here. If delta H is negative, the system loses energy, and the reaction is exothermic. That's review from Chapter 5. If it's positive, delta H positive, the system gains energy, and the reaction is endothermic. The vaporization of liquid water to steam, is that endo or exothermic? To turn water into steam, into a gas, you have to add heat, add energy. So that is an endothermic process. In what temperature range is it great? Is it a spontaneous process? So when does it happen? Well, the temperature has to be greater than its boiling point, right? 100 degrees C, and it's non-spontaneous at less than 100 degrees C. It doesn't do that. Is ice melting spontaneous at room temperature? Yes, right? Unless, well, inside, yes. Is it spontaneous at negative 20? No, it's too cold. It stays ice. The normal boil, I'm going to skip that one. What is the second law of thermodynamics? You can look that up. Would each of the following changes increase, decrease, or have no effect on the number of microstates available to a system? And remember, the number of microstates is directly related to the entropy. If you increase the temperature, that increases the energy in the molecules. It makes them move around faster. So that would increase microstates. Decrease volume gives them less room, less spots to go, so that would decrease. Change from a liquid to a gas. Solids have the least microstates, the least entropy. Gases have the most, so going from a liquid to a gas would increase that. Would you expect the sign of delta S in a chemical reaction in which 2 molecules of gaseous reactants are converted to 3 moles? 2 moles to 3 moles. More moles of gas is more entropy. So delta S would be positive. Increased entropy. When 2 gases combine to form a solid, delta S is going to be negative, right? We're losing entropy. They're getting tied together there. Does the entropy of a system increase, decrease, or stay the same when the temperature increases? Temperature increases, entropy increases. I think we already did that. The volume of a gas increases. If you increase the volume, that gives it more room to fly around. That's more entropy. Equal volumes of ethanol and water are mixed to form... No, don't worry about that one. I don't need that. For each of the following pairs, indicate which substance possesses the larger standard entropy. So when we're looking at these, you either want more atoms, bigger atoms, more atoms in the molecule, things like that. So a mole of P4 or 1 mole of AS4, that's hard to know, but AS4 is bigger. It's a bigger atom, so it's going to have more entropy. Helium at 3 atm or helium at 1.5 atm. The more pressure you put on a gas, the more constricted it is, so the lower pressure is going to have the higher entropy. And 1 mole of neon at 15 liters and 1 mole of neon in 1.5 liters. More volume, more entropy. Here, standard entropy, more atoms is more entropy. So C2H6 has more microstates than C2H2, as does CO2. Calculate the delta S values from Appendix C. So here I just gave you the table here. These problems are, it's the sum of the delta S of times the coefficient. You got to remember to multiply by the coefficients of the products minus the sum of the delta S's of the reactants. So for this one, the reactant, we only have one, NH4NO3. It's 151 minus the products. We have 1 HNO3, 266.4, plus the NH3, 192.5. And you do that math out, and you get negative 307.9 joules per mole Kelvin. Just be careful with the calculator there. I'd always do this first. For the bottom one, I'm just going to lay it out here. Products minus reactants times their coefficients. So you got to remember the coefficients in there. Products 4Fe. So it's 4 times whatever Fe is, 27.15, plus 3 O2s times 2O5 minus the reactant 2 Fe2O3 is 89.96. Alright, you do that out, and really what do you get there? You get 108.6 plus 615 minus 179.92, and that's going to equal 543.68 joules per mole Kelvin. So this is really just watch your calculator there. That's the big part of the problem there. All right, here are some delta G reactions, right? Delta G tells us if something is spontaneous or not spontaneous at a given temperature. So the delta G formula, which will be given on the exam, as was that the sum of those formulas, the sum of the products minus the sum of the reactants that'll be given. This one's delta G equals delta H minus T delta S. All right, is the reaction, so it has a delta H of negative 35.4 and a delta S of positive 52.4. Is this reaction exothermic or endothermic? Delta H is negative, so it's exothermic. Does the reaction lead to an increase or decrease in the randomness or disorder of the system? Delta S is positive, so that's increase entropy or randomness. Calculate delta G. Delta G equals delta H. And really only the trick here, 35.4 kilojoules minus T. What's the temperature? We don't know. 298 K. Temperature has to be in Kelvin. And your delta S has to be in, you put it in kilojoules. It's in joules. So you have to convert. Remember that, 0.0524 kilojoules per Kelvin or moles Kelvin, whatever it includes in there. All right, and then we get that, so that is negative 35.4 kilojoules minus 15.6 kilojoules per K, and that gives me a negative 51.0 kilojoules. If delta G is negative, that is spontaneous at that temperature. And something that is has a negative enthalpy, a negative delta H and a positive delta S, is always spontaneous. All right, that's fact. Number 16, it's the Gibbs free energy, the delta G. It's the same as the delta S, right? When you're using the table, it's products minus reactants times their coefficients. So I'm going to spare you that one. And down here we have 17. For the values given for delta H, delta S, calculate delta G. If the reaction is not spontaneous under standard conditions at 298, at what temperature would it become spontaneous? So if I look here, again, we put in our delta G equals delta H minus T delta S. And for this first one, it's negative 844. Minus 298K times, remember again to convert, it's negative 0.165 kilojoules per Kelvin. And if you add that up, you get negative 794.83 kilojoules. So this is already spontaneous. The second one here, we do delta G equals delta H minus T delta S. Plug in your delta H. Now we have a very large endothermic reaction here. You also have a positive delta S, so that could be spontaneous. It's 298 times 179. And we get a, 0.179, excuse me. Convert to kilojoules. And that's 519 kilojoules. Positive, so it's not spontaneous. So if a question asks you like this, or the question just straight up asks you, at what temperature would this become spontaneous, right? Higher than what temperature? The line is 0, right? When delta G is at 0, that's at equilibrium. So if you set your delta G equal to 0, and you plug in your other values for delta H, which is 572 kilojoules, and then you solve for the temperature. What temperature will this equal 0? All right, we plug in our other values here, and then you get, right, negative 572, right? I subtract 572 from the other side is equal to negative 0.179 T. T equals, then it's a positive 3,201 K. So that's when it would be at equilibrium. So the temperature greater than that, this would be a spontaneous reaction. So not for a long time.